Hello, it's astronomy time again. Welcome to the winter program for United Astronomy Clubs of New Jersey. Tonight's presentation is Speckle Interferometry of Double Stars, presented by Clif Ashcraft. Cliff is a retired chemist who specialized in organic and polymer synthesis, earning a PhD from Berkeley and a BS from University of Cincinnati. He enjoys singing tenor with the Philharmonica, building telescopes, taking planetary images with a webcam, double star observation, and hanging out with his observatory guard dog, Chewie. Cliff serves on the research committee of Amateur Astronomers Incorporated and enjoys making presentations on a variety of astronomy topics. Our topic tonight is Speckle Interferometry, and I'm sorry if I'm butchering that pronunciation. It is a technique for measuring the separation and position angles of very close double stars, even under poor seeing conditions. Before, it had been solely the area of professional astronomers having access to expensive, low read noise cameras costing way more than I can make in a year. And now you can do the same sort of work in your backyard with a CMOS video camera costing about $350 or less, and telescopes already available to amateur astronomers. With that, I would like to remind you that I will be monitoring chat for any questions that you may have that we will ask at the end of the presentation in a brief question and answer session. And with that, welcome, Cliff.
Thank you. Speckle interferometry of double stars. Well, why bother with double stars in the first place? Well, double stars orbit each other in accordance with Kepler's laws, and if you observe them over a long enough time, you can determine their orbital periods. From their orbital periods and their distance, you can weigh the stars. The mass of stars is fundamental to any astrophysical understanding of how stars work. Now, the period and separation of double stars are related. At typical stellar distances, binary stars with wide separations have periods lasting hundreds of years. Life is just too short to get much information from them. The closer the binaries are, the shorter the periods. You get more bang for the buck observing very close binary stars. It takes less time to get the data to compute an orbit. Now, the trouble is, the closer they are, the harder they are to observe. Atmospheric turbulence limits the resolving power of Earth-based telescopes. That's why the Hubble is in orbit. Now, if binaries are much closer than 1 second of arc, they're almost impossible to measure, and the problem is worse for doubles where one of the components is much brighter than the other. Now, here's a typical binary star system that's been observed since way back in 1825. It has a period of 87.7 years, and the second component moves in the direction of the red arrow. It was discovered in 1778 by William Herschel. It's 70 Ophiuchi, or otherwise known to us double star astronomers as WDS 18055 plus 0230. That's just the catalog number in the Washington double star system. It's also called STF 2272AB, and it has a distance of 16.6 light years. The separation is 6.2 arc seconds at its furthest point, but it could get a lot closer than that, around 2 arc seconds, when it swings around at periasteron. The position angle, this angle theta, measured from the north by way of the east to the line connecting the two of them, is 128 degrees. An observation of a double star in a binary star system consists of determining this distance called rho and this angle called theta. Now, how have double stars been observed? Well, the first method is just using your naked eyeball. Hey, that star looks like there's two of them really close together. And examples of double stars discovered this way are Alcor and Mizar in the handle of the Big Dipper, and Epsilon Lyrae, the double-double. Also, visual telescope observation comparing the star size with the separation and estimates of the position angle. William Herschel's first attempts at measurements of separation and position angles were based on this method. It's very poor because the star size depends upon seeing and the aperture of the instrument and how well it was made. Now, visual measurement using micrometers of various types. This was initiated by John Herschel, William's son, and many others in the classical period. Now, it's limited by seeing, aperture size, visual acuity, and technique. In this procedure, you move a movable crosshair uh, with a delicate worm drive, and you measure the separation of the two stars by comparing the separation of two spider webs inside of the filar micrometer. And an angle around the outside of it is used to determine the position angle. Now, this method was used to build the database upon which the WDS is based. It's not accurate for sub-arcsecond separations. Spectroscopy. You can observe periodic shifts in the frequencies of the absorption lines in spectra of stars caused by Doppler shift due to orbital motion. Now, this is excellent for very close doubles with very short periods, ones where you can't even resolve the other component. You could also do astrometry of charge coupled device images. Now, this is the method that I, Jim Daly, and other amateurs used for papers published in the Journal of Double Star Observing in the 1990 to 2015 timeframe. An example would be my paper in JDSO Volume 3, Number 2, spring of 2007. Now, this method is limited by seeing and the digital sampling of the detector to separations of several arc seconds, but it's still useful and you can get good data this way. The final one I'm going to talk about is Speckle interferometry. This has traditionally only been used by professional astronomers, chiefly at the U.S. Naval Observatory. It's excellent for sub-arcsecond separations, and it bridges the gap between micrometric and spectroscopic data. Trouble is, you need expensive cameras, large aperture telescopes, and it's limited only by the telescope resolution. Recent availability of low read noise, low-cost CMOS video cameras makes this now a method that we amateur astronomers can use. See my papers in the March 2016 issue of the Journal of Double Star Observation. And last but not least, astrometry by all-sky space missions like Hipparcos and Gaia. These are basically flooding the catalogs with new double star observations all the time. Now, what is speckle interferometry? Well, it's a way to observe double stars that are far too close together to be resolved by ordinary optical observation in the presence of a turbulent atmosphere. Atmospheric turbulence breaks up a star image into a rapidly changing blob of points called speckles, each one of which is an image of the star formed by a sub-aperture lenslets in the air called Freed cells. It's also what causes stars to twinkle. Now, although you cannot see it, all of the information about the separation and position angle of a double star is present in those speckles and can be extracted if you use a lot of math and computer processing. It could normally be done only with very expensive cameras, 2-meter class telescopes, and mainframe computers, way out of the reach of amateurs. Okay, now here is a typical double star. It's Washington double star catalog number 23103 plus 3229, and the discoverer designation is BU 385AB. It has a position angle, or theta, of 85 degrees. This is measured from the north by east towards the line between the two stars, and a separation, or rho, of 0.63 arc seconds. Now, BU 385AB is a discoverer code for S.W. Burnham, who did his observations back in the classical era using Filer micrometers. These numbers tell you that the star is at 23 hours, 10.3 minutes right ascension, and at plus 32 degrees, 29 minutes declination. Okay, now if we could put our telescope in orbit, and I've computed this for an 11-inch telescope like the one that I'm using, what you would see is these two overlapping diffraction patterns. And you can imagine that you could do a pretty good job of that with enough magnification and a Filer micrometer. But unfortunately, we're not in orbit. And what we typically see is this mess. This blob right here is a mass of speckles concealing the fact that we're really looking at two stars. Uh, and there's no real hint of anything that you can measure. Now, this is the frames of a video that I took. Normally, I take a sequence of FITS files, but if you displayed them end to end, it would look like this. Each image is a two-dimensional matrix A of intensity values of each pixel. We compute the Fourier transform, B, for each image, and then the modulus squared of each of the Fourier transforms. We then average those over all of the images we took, and we get something called the power spectral density, which you can see already has some information in it. You notice that there's something that looks like fringes lined up in this direction, which is perpendicular to the line between the two stars, and maybe the spacing of those would have some meaning about the separation. Well, the final step is you take the reverse Fourier transform of this thing that looks like an image, and you end up with something called an autocorrelogram. This is the inverse fast Fourier transform of the power spectral density. And from this autocorrelogram, you can measure the properties of the double star with a great deal of accuracy. You can see that this corresponds very nicely to this diagram, which resembles the original one of the double star. But the trouble is, we can measure the separation very accurately. We got two things we can measure. Both of them give the separation, but we don't know what the theta is. It might be this, and it might be all the way around to this. This is the 180-degree phase ambiguity that Speckle interferometry has, and it's caused by this operation doing the modulus squared, where you you essentially multiply a matrix by its complex conjugate, and that wipes out the phase information. So you don't know whether this spot or this spot is the one that you should measure. Well, that's not that much of a problem because most of these stars have some history. They've been measured before, and we know which side of the primary the secondary star is. Or if it's a new star, one might get information by, say, using lucky imaging to find a little blob on one side or the other that would tell you which of the two values for theta that you're to use. Well, now, what had been needed to do speckle interferometry? Well, the first obstacle is you need an electron multiplying charge coupled device camera. A cheap one is $14,000, but the one the real guys like to use costs $50,000. The reason you have to use those is they're extremely low read noise. Uh, Noise in the image competes with the speckles and limits your ability to actually see the stars properly. They also tended to use 2-meter class telescopes, a lot bigger than most of us actually have, although some amateurs are getting pretty big backyard telescopes these days. You need access to a mainframe computer and higher math skills to deal with all those fast Fourier transforms and matrix multiplications and the like, and probably Fortran programming skills back in the day. Now, this pretty much limited the activity to professional astronomers and their graduate students who had access to all of the above expensive stuff. Now, most of the work was done by the professionals at the U.S. Naval Observatory working with Dr. Bryant Mason. Well, what works today is a lot different. A $350 CMOS video camera with very low read noise, like the ASI 224MC or these others. Any good telescope, preferably equatorially driven, for example, a 6-inch f8 on a German equatorial mounting, or what I used, a C11 Edge HD on a fork mount, or a C14, or the 24-inch Ritchie Chrétien at Sperry Observatory. They would all do just fine. Access to a decent PC with lots of hard disk space. You don't need a mainframe computer anymore. And most importantly, David Rowe's Speckle Toolbox. Now, I don't know if you know David Rowe. He's the chief technologist at Plane Wave Instruments, and one hell of a computer programmer as well. And he created the Speckle Toolbox and made it available to us members of the Speckle Interferometry group. You could download it there after you join. And it used to be a Yahoo group, but now it's a groups.io called Speckle Interferometry Topics. Resolution is limited only by the diffraction limit of your telescope aperture. For example, a 6-inch telescope can resolve 1 arcsecond. My 11-inch, about a half an arcsecond. A 14-inch, 4/10 of an arcsecond. And a 24-inch would do a quarter of an arcsecond. So you get the full resolving power of your optics in spite of atmospheric seeing. And you don't even have to know what a Fourier transform is, because that's all built into the free software. Now here is my speckle interferometry setup that I use for the data for my publications. The telescope is a Celestron C11 Edge HD. It has an f10 focus and really nice optics. It has a 10x visual finder. It's on a fork equatorial mount. There's my dew shield, guide scope, which I don't use for speckle interferometry, and a video finder, which I do use a lot. This one is based on an imaging source DMK21 camera, what I used to use for planetary imaging, but which was replaced by this ASI 224MC. It's got a 55 millimeter camera lens on it, intended for a video camera. And its purpose is to help me find both the double stars and the comparison stars that I need to use. I'll show you that later. Motorized focuser is critical both for this work and for the planetary imaging that I do. And it's very difficult to manually focus something when you're working at such high magnifications. I use a 3x Barlow lens to blow the thing up to about f30, which you need for good sampling of the speckles. The main camera is an ASI 224MC, and there's my hand controller for the mount. My computer is over here to the side of this observatory room, close to, but convenient to get USB cables and the like over to it. Camera calibration. The setup I use for speckle interferometry is essentially identical to what I use for planetary imaging by the Lucky imaging method. However, there's one essential difference. We need to calibrate the camera. That means determine what the camera rotation angle is with respect to celestial north and what the image scale is, because we're going to get real data from this. Here are some ways to do it. Well, you could measure some known double stars and calculate from what the known values were, how much to correct your measurements to get the right answer. You could use a coarse diffraction grating that would generate a multiple order spectrum from which you could calculate your image scale by counting the blobs and doing a little bit of math. But there's a much better procedure called drift image analysis, and that's what I use, and it's built into the Speckle toolbox. Drift calibration coming up. I'm using Alpharats, which is at a declination of 29 degrees, 5 minutes, 27 seconds. What you do is you point your telescope at the star, get it on one side of your field, start imaging, taking a whole series of FITS files, and turn your drive off. And when you turn your drive off, the star begins to drift across the field. Meanwhile, your camera is furiously taking a whole big folder full of FITS files, which we're going to feed to the routine in the Speckle toolbox after we collect the data. So we let it drift across and take lots of pictures. Now we run the drift analysis tool in the Speckle toolbox. This was also written by David Rowe. First thing you do is the software measures the location of the star on your sensor as a function of time and calculates the slope of the drift in the x direction as a function of time. In this case, it's the negative slope, and it's 148.95 pixels per second. You do the same thing in the y direction. In this case, the slope, also negative, is 25.88 pixels per second. Now, from this handy little formula here, you can calculate the actual slope in not in xy, but the direction the star is moving in pixels per second of time, which turns out to be 151.19 pixels per second. Now, knowing that one sidereal hour is 15 degrees at the equator, and it's 15 times the cosine of declination in degrees of arc at wherever your star is, and further knowing that there's 3,590.2 seconds of time per this many seconds of arc, you've got enough information to calculate your scale factor. Now, if you look at X versus Y, the slope of that line is just the tangent of the camera angle. Well, the program measures all that and puts it together in a little chart. And here we find that the camera angle is minus 9.86 degrees, and the image scale is 0.08694 arc seconds per pixel. We're going to need that in the photometry section where we measure those autocorrelograms. Here's a blow up of the field of the tool. You'll need to write down this value and this value here. And this RMS star diameter gives you a measure of the seeing. So this is nowhere near 1 second quality seeing, but we're still going to beat it on our measurements anyway. It's absolute, depends only upon the rotation of the Earth, and it's pretty easy to do thanks to the software. Well, here's my work process for imaging doubles and the reference stars that go with them. Plan targets for the night's run from Washington Double Star Catalog. I tended to work the neglected doubles section because those are the ones that are needed the most to fill in the blanks in the catalog. Run my software on the observatory computer. I always have an Excel or open office spreadsheet on hand to put target data, time of capture, exposure, etc. Put my notes in. I use fire capture for operating the main camera, the ASI 224MC, and I have it set to save FITS files, not to save video, not to save bitmaps, but to save FITS files because that's what Dave's program wants. I also have the remote focus software running so I can control that from my computer. And I run IC capture for this DMK21 video finder camera. I also have a nifty piece of software called Owl's Reticule. It's programmed by one of the Australian amateur astronomers. That gives you a crosshair overlay on the DMK21 screen, which I could use to locate exactly where the center of my main camera screen is located. I also love the Guide 9 planetarium program to help me find things, but you could use the SkyX, it works just fine also. First thing I do is do a drift calibration using fire capture and a convenient bright star to get my camera angle and plate scale for tonight. For example, if I had moved that Barlow lens camera combination even a little bit, it could screw up my results. So I do this every night. Now go to the coordinates of the target star using the planetarium program. Identify the target by right-clicking on a star and reading the information on the screen. Guide 9 has even got the Washington Double Star catalog into it, so it's very convenient for my purpose. Okay, use the telescope hand control to go to the star's coordinates. Now, this is where the video finder comes in. It's now looking at about a 2-degree across field of view, which is now looking at the same thing that my planetarium is looking at. With both of these tools at my disposal, it's very easy now to use the hand control to center the target star on the reticule, Al's reticule's crosshairs on my finder screen. I have both of them displayed on the same screen, and I'll show you that in a little bit. Now, find the star on the full screen of fire capture with the image from the main scope. Now, this can be a pretty big field from the ASI 224. It's got a good size sensor eye. Once I find my star, it'll be sitting there speckling and twinkling. I drag a roughly 256 by 256 pixel or smaller region of interest around it. Now, the only reason to do that is I don't want anything to be imaged other than my target, and I want to have as short an exposure as possible. The smaller the ROI, the shorter your exposure can be because it's limited by the download time from the camera. Adjust exposure and gain to give about 25% saturated histogram. You don't want to oversaturate the bright speckles because that's where most of the information is stored. Now, I routinely take 10,000 FITS images of the target star. The reason is I, I want to make 10 determinations of the position, angle, and the separation and take the average to give a more accurate value to report. Uh, I also need to identify a suitable reference star about the same brightness as the double star using the planetarium and video finder. Um, you better not pick a double star. That's why it's nice to have the catalogs built into Guide 9. It should be a single star, similar brightness to the double star, and fairly close to it in the sky, so the seeing and atmospheric dispersion, etc., will be similar. Go to it using the hand controller and the video finder, and I routinely take 2,000 FITS files of the reference star. The software will use this for deconvolution and sharpening up the images. Now here's my very messy screen on my observatory computer. This is the IC capture screen, and you can see these are the stars that are actually, this is actually an image of the sky, and here are the crosshairs of Al's reticule that I have dragged into position on the screen, and I previously determined by looking at a bright star that where they intersect is going to be within the field of view of the main scope. And I have it actually pointed to TDT 3890, which is one of my target double stars. See, it's not a very bright star compared to these other typically fifth or sixth magnitude stars you see here. It's a very faint one. Now, this is the fire capture screen from the main camera. And this blob of speckles is actually the data from this star. This other stuff is background noise. And the only reason I can do it with this camera is that this is a lot less than you would typically see for an ordinary CCD camera at the high gain settings that I normally would use. Of course, this panel is for setting your exposure. This was a very faint star, so I was using a 50 millisecond exposure and full gain to do this. You can see that I have it set for 10,000 frames. I've not got any filters on it, so this is white light we're using. And here's my histogram. It's on the order of around 25%. Lurking in the background is my Guide 9 screen, and you can see, notice 1, 2, 3 stars in a row. Well, there they are as actually seen by my video finder, and my target right here, which I've identified by right-clicking on it, is the one that's on the crosshairs. So I could be absolutely sure that what I'm looking at is the star that I want to measure. Here's a blow-up of the data that Guide 9 gives you about the thing you've right-clicked on. And you can see that it's in the WDS catalog, and there's the discoverer's ID, TDT 3890. I don't know who TDT is, but whoever he or she is, they measured this star once upon a time. So there's all the data on it. Here again is a blow up of the finder field of view with my target star centered. Now my work process is to, as I said before, use the drift calibration tool, make FITS cubes of the data. Now, A FITS cube is just a bucket full of FITS files. And I create 10 FITS cubes from the 10,000 frames. So I get 10 cubes each, a bucket of 1,000 frames. And I make one FITS cube from all 2,000 taken for the reference star. I use the tool in the Speckle toolbox called Process FITS Cubes on all 11 cubes, 10 from the target, 1 from the reference. What this does is do the two-dimensional discrete Fourier transform of each FITS file in the cube. Then it computes the modulus squared of each transform FITS file. The modulus squared is just the Fourier transform multiplied by the complex conjugate of the Fourier transform. All of these are matrices roughly corresponding to the rectangular area of the image. Then you compute the average modulus squared over the entire whole FITS cube. So the data from the speckles from 1,000 images are in this modulus squared. That gives you that power spectral density that looked like it had some faint fringes in it. Now, you don't have to worry about the math because it all happens to all of your cubes at once. It makes me tired just thinking of all the math that the poor computer has to do. Now, make the measurements. There's a speckle reduction tool, which is actually a photometric device in the toolbox. You load the PSD file of both the target star and the reference star, and this lets you look at either the fringes of the interferogram, display PSD, and while looking at that, you adjust high pass and low pass filters and the percentage of the deconvolution star you want to use to get optimal contrast of the fringes and the best resolution in the autocorrelogram. This is kind of a fiddly step, and it takes some practice to learn how to use it, but once you learn it, you can do it pretty quickly. Now, you use the astrometry tool on the autocorrelogram to extract both the theta and the rho of the target star, assuming that you haven't forgotten to tell the tool what the camera angle and the image scale you got from your calibration. It's basically you just type it into a little data box. Okay, here is what you are looking at when you're setting up the measurement of an autocorrelogram. Here are the filter adjustments that you set up to get the optimum resolution of the autocorrelogram. And here's setting the how much of the reference star you're using. By the way, using this tool up here, you load in your process FITS cube of the double star, and using this, you load in the process FITS cube of the reference star to be used for deconvolution. Now, then you come down to the photometric tools, and you could either make it dimmer or brighter or smaller or larger, and you could pick this little target tool, and when you do that, you have the option of moving it around, or it will often just lock right on one or the other of these two satellite images from which you will make your measurements of theta and rho. Once you do that, it now gives you the photometry screen, and this single determination gives you the theta of 265.518 degrees and a rho of 0.4644 arc seconds. Now, I want you to look at this. This is pretty easy to measure, and yet it is very close to the resolution limit of my 11-inch telescope. 0.42 arc seconds. This is 0.46 arc seconds. One would never be able to do that uh, just looking at the image with a filar micrometer. Now, once you've done that, tabulate all 10 values in your spreadsheet, compute averages and standard deviations, communicate the results with fellow double star enthusiasts, particularly the ones at the U.S. Naval Observatory are keeping track of all this. Tell the guys on the Yahoo group, which unfortunately is defunct. It's now one of those AP group things, but it got converted. Publish papers and give talks to interested folks like you. Here's some of my typical data. Here's one that didn't work. This was just too darn close. And the funny thing was the value in the double star catalog suggested I should be able to observe this. So all I could tell it is that the row is less than 0.76 arc seconds, probably a lot less. Here's one where I got a very good measurement on, and you can see that this has a row of 0.65 arc seconds, and again, very clear autocorrelogram, very easy to observe. And here's one with a row of 0.73 arc seconds. Again, very easy to observe. Here's a typical night's run tabulated in an Excel spreadsheet. Here's my Washington double star catalog number, the discovery designation, when it was observed first, when it was observed last, the catalog values on it, and here's my observations. Add comments on whether I got a good lock or whether I had to fiddle to get the measurement. So, you can see there's multiple tabs for different nights. So I did an awful lot of observations using this method. On a good night, I could measure anywhere from 5 to 7 doubles, and that includes getting the 10,000 frames for the double and 2,000 frames for the comparison star, each one. Measures to the time that I did this talk, which was a while back, each of these stars is a star that I successfully measured the separation and position angle. And so we're plotting separation versus primary magnitude of the star. And you notice that I've got a floor of around 4/10 of an arc second, and it would be really surprising if I claimed to measure things down here, because that's better than the resolving power of my telescope, and this is not magic. You cannot beat the diffraction limit of your telescope. But I came pretty darn close to it with these 4 observations, and these were no slouches either. I also have a brick wall here at around magnitude 11. That is a combination of an aperture limit and a New Jersey sky pollution limit. I'm sure that if I were in the west of Texas, I could get a bit further, maybe out to 12 or 13th magnitude. Now, papers that have already come out of this activity. There was a group paper. This is with Russell Genet, Dave Rowe, myself, Sam Wen, Benoit Schillings, Richard Harshaw, and Jimmy Ray. All these guys, except me, had been working together, attempting to do speckle interferometry, borrowing one of those electron multiplied CCD cameras. And I bumped into a discussion among them on one of the discussion groups. And they were all excited because it looked like there were going to be some relatively inexpensive cameras available soon that could be afforded by amateurs. Well, I noticed they were talking about this ASI 224. Well, damn, I had been using that for a couple months already for planetary imaging. So I fired off an email or two and a couple of phone conversations, and I told them that I would be just tickled to try this technique out. if they'd give me some targets to try and maybe help me with the processing. Well, they set me up with a copy of the Speckle toolbox, and pretty soon the paper that these guys were going to give at the annual conference on double and multiple star observations in Barcelona, Spain, where they were going to say, "Wow, folks, pretty soon we're going to be able to do this," turned into a, "Hey guys, we did it. It works." So for that effort, they put my name on the paper. I didn't write the paper, they did. They were just absolutely tickled that I was able to measure A592 with my 11-inch telescope. It's only 6/10 of an arc second across, and they were just amazed that I was able to do that. I published my own paper in the same issue of the Journal of Double Star Observation on all of those observations that I made that I showed you on that chart. And here is a table comparing my measure of theta with the last reported value in the Washington Double Star catalog. And you can see generally it's a perfect 45-degree line showing a perfect fit with a couple of notable exceptions. And I think it's turning out that the star has been moving and the old value in the table was just basically out of date. Same thing for my measure of rho. Uh, Last reported value in the Washington Double Star catalog. There's a little bit more scatter in the measure of separation because particularly down in the low values here, because we're pushing the diffraction limit of the optics. Here's some pictures of my autocorrelograms compared with lucky imaging results. This is basically the same technique I use for planetary imaging, but applied to double stars. Now you can see that, well, it's pretty obvious. I'm supposed to use this one because that's which side of the double star the secondary component actually is. It gets harder as they get closer together. For example, at 0.71 arc seconds, I get a beautiful autocorrelogram, easy to measure, but I can just barely tell it's a double because there's a lump on this side of the brighter object. So anyhow, accomplishments to date, I've got this paper on using conventional CCD imaging of double stars back in 2006. I've made over 300 double star measurements that are now listed in the WDS, including 20 newly discovered ones that got my initials on it. I've contributed Speckle observation results to that international meeting in Barcelona, Spain, and I have my own paper on that set of objects that I told you about before. Uh, uh, I've measured over 60 close doubles using Speckle interferometry, many of them with separations below 1 second of arc. I intend to get a little bit better resolution by continuing the work on my C14, which ought to get me down to a little bit lower than a half an arc second. That's pretty much all I've got to say, and I'd be happy to take any questions you have.
Thank you so much, Cliff. At this time, I would welcome any people who are currently in chat if they have any questions about speckle interferometry. I always have trouble saying that. um, and while I'm waiting, if there are any questions, actually, there is one from earlier. I believe someone had mentioned and asked the Centauri system. That is a binary system, correct?
Centauri system.
Yes.
Certainly, but I can't see it from here. But if it were above the horizon, I would be able to uh, certainly measure the two components of Alpha Centauri. I don't know if I would be able to see Proxima through the light polluted New Jersey skies. It's pretty faint.
All right. Another question I have personally, um, when you were first starting out using the software, was it somewhat user friendly, or did you find that you needed a good bit of help learning what was what and what you needed to do to set it up?
Well, it was all pretty easy and straightforward, except the business of adjusting those low pass and high pass filters uh, with the photometry tool. That took a little bit of getting used to, but once I figured out the right values to start with, I could usually zero in on it pretty quickly. So, but I had the advantage of being able to email Dave Rowe and get help when I ran into a jam. But it was the business of doing the heavy duty math, converting the set of images into the Fitz cubes and processing the Fitz cubes. That all worked just as easy as a top. No problem with that at all. And I was already doing essentially the same kind of imaging for my planetary work. So there was a very good overlap in observational technique. So if you've done planetary imaging using fire capture to get AVI files, all you got to do is turn it over to make FITS files, and instead of looking at planets, look at doubles. You collect your data the same way, and then you're just over to using the toolbox.
All right. Should any of our online audience want to start using uh, the programs and whatnot and start getting into this, um, I know you had mentioned several times there are a group. Are those groups open to the public, or would they have to like apply for access?
To get access to the files so you can download the program, you need to join, but it's free. So it's I put in let's see, it's one of those
If it would make it easier, if you send us the that link on how to join or whatnot, we can add that into the description down below after the presentation,
okay.
and that way it makes it very easy for anyone who would like to start trying this or try their hand, uh, to be able to find those links to get the tools they need.
Okay, I'm looking for it. There you go. There, I better share this again. Let's see. How do I share? Ah, there we go. Share and share that again. Okay, now you see this one slide. I will blow it up. There we go. Uh, it's groups.io slash G slash Speckle Interferometry slash topics. And if you go to this link, you will encounter that group, and probably you can read any discussion that's already there. But to get access to the files, I believe you have to actually join the group. And Dave Rowe is the moderator of the group, and I'm sure he'll be tickled to have uh, another speckler join the ranks of uh, measuring the all the double stars that need to be measured.
All right. It appears that I've exhausted the questions from our online audience. I want to thank you for a great talk, and I want to thank everyone for tuning in. Don't forget to hit the follow and subscribe buttons down below on our channel so that you could join in next time. Our next presentation is going to be the first Saturday of January, and that's going to be What's Up in the January Sky with Lonnie Bunis. Also, check us out on our website, uacnj.org. And we have social media through Facebook and Instagram and Twitter. I want to thank you all, and until the next time, have a good night.